So, there are many different wavelengths of radiation. And the sun, being hot, is emitting what's called shortwave radiation. The Earth, relatively being cold, emits longwave radiation. Typically, the way it works is shortwave radiation is visible light and everything shorter than it. Longwave radiation is everything longer than visible light. Well, there are certain gases in our atmosphere that are what are called selective absorbers. And the way that this works is that they absorb some wavelengths of radiation, but not others. And so what I actually have here, and let me pull out my little laser pointer, is this graph actually shows the different types of gases in the atmosphere. So we have oxygen, water vapor, carbon dioxide, nitrous oxide, and methane. And then down here is the total atmosphere. And the way that this actually works is whenever you see a purple area, that purple area represents absorption. So for example, let's look at nitrous oxide. So for nitrous oxide, there's no absorption happening in the shortwave, no absorption in visible light, and then as the wavelengths get longer, so around 1 micrometer, nothing really. Right around 3, we see a little spike. And then right around 5, we see a huge spike to almost 100%. This means that 100% or almost 100% of the radiation that makes contact with nitrous oxide at this wavelength is being absorbed. So radiation with a wavelength of 5 micrometers is being absorbed by nitrous oxide. And then we see another one right around 7, maybe 7.5 micrometers. Now, based on that, take a look at these other gases, and which ones are, or which wavelengths are being absorbed the most by them. If you actually take a look, molecular oxygen and ozone absorb a lot of shortwave radiation, and in fact, this is why the ozone layer is so important, because it is that layer that is absorbing all of those deadly UV rays. But then as you go towards the long wave, not a whole lot of long wave radiation is being absorbed by oxygen, with the exception of right here at 10 micrometers. It's a lot being absorbed there. And then take a look at a few of these other ones. Water vapor, no short wave, lots of long wave. Carbon dioxide, no short wave, lots of long wave. And then here's the total atmosphere. And if you remember, what I mentioned earlier is that humans emit right around 10 micrometers. Humans emit right around 10 micrometers. The Earth is a little bit closer to 11 to 12 micrometers. And then cooler parts of the Earth emit longer wavelengths. So, sorry, clearing my throat right there. And water vapor and carbon dioxide actually absorb a lot of the radiation that the Earth gives off. And then finally, right down here, this is the total atmosphere. And there's this one area, roughly between 7 to 12, 13 micrometers, where most radiation is being allowed to pass through. If you notice, very little purple here, very little purple here, just with the exception of right around 10 micrometers. This is what is called the atmospheric window. Now, the very last thing I'll talk about for this investigation is this property called albedo. Some objects don't absorb radiation, but instead reflect it. And if you've ever been outside and stood over a white piece of paper, or if you've tried to read a white piece of paper while sitting outside and it blinds you, the reason why it does that is because that white sheet of paper is reflecting most of the sunlight that's hitting it. On the other hand, something that's darker doesn't do that because it's absorbing most of the sunlight that hits it. And the albedo basically tells us how much radiation an object reflects. Light-colored objects reflect most of the radiation that hit them. On the other hand, dark-colored objects absorb most of the radiation that hit them. They don't reflect it. And this is actually just an interesting application. This is why on a really hot day, you want to wear a light-colored shirt, not a dark-colored shirt. Because if you wear a light-colored shirt, that is going to keep you nice and cool because most radiation is being reflected off of you. On the other hand, if you wear a dark t-shirt, most of that radiation is being absorbed. Radiation that's absorbed causes heating. That's heating your body up.